I want now to go to another topic in a high level as well. And this is Professor Nazeeruddin from Switzerland. He will talk about the development of efficient and stable perovskite solar cell and module. So it's a stability, which is very important. I just want to give some, normally I don't need to talk about who is Nazeeruddin, but I have to do it here in order that some people don't know him. They know Nazeeruddin is a professor of chemistry at EPFL. EPFL is École de Lausanne, École Polytechnique Fédérale de Lausanne. He's a Sion campus, and his current research at EPFL focuses on perovskite solar cell and light emitting diodes. Two very important topics for the application. He has published more than 785 peer-reviewed papers, 10 book chapters, and he's the co-inventor of over 90 patents. His work with a high impact has been recognized by invitation to speak at over 300 international conferences. He appeared in the ISI listing of most cited chemists and has more than 150 335 citation with an H index of 171. So he's belong to the most cited researcher in the world. He teach the functional material course at EPFL. He teach at Korea University. According to the Web of Science in 2016, he is the 5th most cited chemist in the world and is one of the 19 scientists identified by Thomas Reuters at the world most influential scientific mind in 2015. So we are really very lucky to have him with us. He has been named Thomas Reuters highly cited researcher from 2014 to 2021. He listed among the top 10 researchers in the perovskite solar cell research field by Time Higher Education. So today he will talk about perovskite. So we have the best scientists to talk about perovskite. He's directing and managing several industrial, national, and European Union projects. He has been appointed as a world-class university professor by Korea University and adjunct professor by King Abdul Aziz University, Jeddah. He has been elected to the European Academy of Science, Fellow of the Royal Society of Chemistry, and Fellow of Telangana Academy of Science, and has won the 34th Khwarizmi International Award, Laureate in Fundamental Science 2021. So we are really, really happy and lucky to have you, Professor Nazeeruddin, and the floor is yours to talk about your talk on perovskite.
Thank you, Professor Ahmed, for your kind introduction and all the detailed information you have provided to the audience. I really appreciate it. And also, I would like to thank all the organizers who has organized this virtual university seminars. It's very interesting for the community to get the information as the top research what the people are doing in these fields. So with this introduction, I would like to share my presentation. So this is my presentation. I think you will be able to see now. Can you see my presentation?
Yes, sure.
So let me just take my laser pointer. Yeah, so as Professor Ahmed mentioned, the title of my talk is Development of Efficient and Stable Perovskite Solar Cells and Modules. You will see why we should work on the perovskite solar cells compared to silicon solar cells, which are well known in the literature, in the market, with the efficiencies reaching over 26%. With the perovskite solar cells, we can also reach very high efficiencies, but there are problems in the perovskite solar cells and which we are addressing. That's what you will see in my presentation. So my name is Nazeeruddin, and on the bottom you can see my email address. Regarding this presentation, if you have any questions, you can ask it during after my talk, or you can send me email. I will try to respond as soon as possible. Let me just take this camera. Sorry. There's a pointer. So this is our campus, what we are seeing here, and it's located next to the Lake Lemon. It's a very beautiful campus, but I'm located in Sion. That's also a very nice campus with beautiful mountains. I come to the topic, the halide perovskites. What is actually metal halide perovskite? What are the advantage of these materials? So the materials are very simple materials like a salts. So here is the composition which I have given. It's a typical formula of ABX3. A is a monocation. This monocation can be either from inorganic cation series, that's a cesium, it has to be big enough, or organic methylammonium or formidinium. And the central metal, B cation, can be lead 2+ or tin 2+, and the X is a halides. So what happens by using these three materials, when you form the thin films, they spontaneously form self-assembly of perovskite materials having the structure of this three-dimensional material. But these materials, they have a very interesting properties which I have highlighted here on the bottom. The strong light absorption in the visible region, as this is one of the criteria of any semiconductor to work properly. So it absorbs all the visible light. In the next slide, you will see how the absorption spectra looks like these materials. And the tunable band gap of these materials. So how do we tune the band gap? So this particular band gap, depending on the materials which we select, cesium or formidinium or lead or tin, bromide, chloride, and halide. So we have a beautiful possibilities to tune the spectral responses from onset from say 1.2 EV to almost 2.25 EV. So you say these materials are highly tunable. The other interesting property of these materials is a small excitation dissociation energy. When you shine the light, these materials, they create charges, and the dissociation energy is so small, the charges are diffused at the contacts. So these are the very interesting properties of these materials. As I mentioned, the absorption spectral properties are shown on the left side of the viewgram. So the onset starts around 800 nanometers and goes up to 400 nanometers. So it absorbs all the visible region of our solar spectrum. And wherever you excite, you will have a very nice emission coming around 820 nanometers. The other interesting property of these materials compared to silicon materials, if you see this purple line is the silicon solar absorption properties, which is very sluggish onset. Compared to gallium arsenide, which has a very sharp onset, the perovskite materials, which are having a similar onset, showing these materials have a well-ordered structure with the low trap state densities. So these are the interesting properties of these materials. Once if you have these materials, there are several device configurations, but for the sake of audience and the students, I have taken two main configurations. One is called PIN, and the second one is called NIP configuration. It's the way you deposit various layers. In the NIP configuration, the light is passing through the whole transporting materials, followed by the perovskite, the light is passing through the electron transport layers, followed by the perovskite, and then the whole transporting material. Therefore, the ETL layer has to be transparent here. In the other case, PIN configuration, the light is passing through the whole transport material, followed by the perovskite and electron transport material. Therefore, one of the main condition is the whole transport material has to be extremely transparent so that you don't lose the light absorption by the charge transport layers. So in these two configurations, the highest efficiency of NIP configuration is 25.7%, reported by Korean scientists. In PAN configuration, very recently, the Faust scientists have reported 24.3% efficiency. So what happens in this configuration? So you have a ETL layer and whole transporting material. In both the cases, the perovskite is sandwiched between the ETL and the whole transporting materials. When the light is shined onto these materials, you immediately instantaneously create charges, positive and negative, and the negative charges are extracted into the ETL layer because of the band alignment. And the positive charges are well aligned with the hole transporting material. So the positive charges are extracted into the hole transporting materials. So this way you collect all the charges at the interface. Now, if you look at the cross-sectional image, the diagram of our perovskite solar cells, on the left side, it's a cartoon. On the right side is a cross-sectional image of one of our cell. So we have a conducting glass, and on which we deposit a very thin layer of compact layer of TiO2, and then followed by we have a ETL layer, that's electron transport layer, composing of mixed oxide, titanium dioxide and tin oxide, and then we deposit perovskite layer of 500 to 600 nanometers thick. Then you have a very thin layer of two-dimensional perovskite. That's a phenylethylamine iodide. So that you will see in coming slides what is two-dimensional perovskite. Followed by you have a hole transport material and gold as a contact. Now, if you look at our composition, in all our compositions, invariably we'll be having a 5 to 10% excess of lead iodide. Why we are using excess of lead iodide? This excess of lead iodide, when we are having the perovskite, when we use this type of larger cations, this forms a thin layer of two-dimensional perovskite. That two-dimensional perovskite layer passivates interfaces and reduces defects. So you will see more details in coming slides. So this is the typical architecture of our devices, NIP and PIN. The cross-section image and the composition is shown here. Now, using this type of configurations in NIP, we have obtained over 24% efficiency, and this efficiency was certified at Newport. The values are exactly tallying with our labs values and the values obtained at Newport. So showing that our measuring system is consistent with the international standards. And now I come to what we can do further. So we have used these materials and made a small mini modules and assembled as a small panel as shown here, A4 size panel. Each mini module has 8 cells. The 8 cells are seriously connected. So as a result, you can see the voltage of this mini panel is 8.2 volts. And all these remaining panels are parallelly connected. And that gives you close to 1 amp short circuit current. So these are the mini modules which we have developed. At the same time, we can also develop flexible perovskite solar cells. Efficiencies are slightly lower than the glass substrate, but this is possible to get high efficiency. So the take-home message from these few slides are the power conversion efficiency of these mini modules. We have reached 22%, over 22% efficiency. The size is shown here for 6.5 into 7 centimeters, resulting 45 square centimeters. But however, what is missing in these solar cells and in these materials is stability. So the stability is the biggest problem in these materials. So you will see our approaches, how we are addressing these stability issues. So I have highlighted our approaches in the following sections. So we are trying to improve the stability by interface engineering, and also we are trying to improve the stability of the perovskite materials by compositional engineering of the materials. And also at the same time, we are developing new charge transporting materials that are more stable than what are known in the literature. And at the end, I will show a cost analysis. If tomorrow you have a funding or some industrial partners interested to go 100 megawatt plants, what would be the manufacturers, the selling price of these materials, the cost analysis, and as well as payback time. So these are the information which I will provide. This is the outline of my presentation. So let's go to my presentation. So here is I'm showing the three-dimensional perovskite. On the top left side is the three-dimensional perovskite structures. Now, in this three-dimensional perovskite, the cation, A cation, is inserted in the cavity of this framework. What happens if the cation is bigger than the particular size, which is dictated by Goldsmith tolerance factor? If we have a bigger cation, then we try to split this three-dimensional perovskite into low-dimensional perovskites. So now this gives you a golden opportunity to tune your material properties by combining different ratios of larger cations and smaller cations, and this gives you controlling of the layer thickness. Here what we call n equals to 1 layer. Here we have 2 layers together separated by the 2-dimensional perovskite. Here we have 3 layers together separated by 2-dimensional perovskite. So what are the 2-dimensional perovskite? What are the cations? So in the middle, I have highlighted some of the two-dimensional perovskite cations, which are organic chemists, but I will not discuss all these cations. I take one example. That's a phenylethylamine. This is one example I am taking. By using this particular cation and other cations that goes into three-dimensional perovskite, now compare the absorption spectral properties. With the three-dimensional perovskite, where the cation goes into the cavity, we have the spectral responses going from 800 nanometers all the way to the whole visible spectrum. On the contrary, if we change the cation of small size, if we use some of these larger cations, we form a two-dimensional perovskite that has a very small absorption in the visible region. But however, three-dimensional perovskite has a less stability compared to the two-dimensional perovskite. So what you will see in my presentation is combining these two strategies. Keep the three-dimensional perovskite and coat with the two-dimensional perovskite to increase the stability. That's what you will see. So if you look at the two-dimensional perovskite absorption spectral properties is shown here. I have taken two examples particularly. Fluorophenylethylamine, this is one cation I have taken example. And the second example I have considered is pentafluorobenzylamine. Why I have taken these cations? You try to remember that fluorinated substituted cations are hydrophobic. Because some of our materials, they are hydroscopic, they tend to take the humidity. So we want to prevent these hydroscopic properties by introducing hydrophobic cations. That's a pentafluorobenzylamine. And here I have reduced to pentafluoro to monofluorobenzylethylamine. So using these two cations, we made the two-dimensional perovskites, which are shown here. The purple one is a pentafluoro, and the green one is a monofluorophenylethylamine two-dimensional perovskite absorption spectral properties. Now, if we deposit these two-dimensional perovskites on top of three-dimensional perovskite, how does the spectral responses look? Now, if you look at the reference sample, that's a black. There is no two-dimensional perovskite on the top. Now we used a two-dimensional perovskite fluorophenylethylamine containing one. That's a blue curve. And now if we use the pentafluoro, that's a red curve. So the spectral properties in the UV part, below 500 part, you can see distinct differences, but onset is mostly dominated by three-dimensional perovskite. So what does it give you having this type of two-dimensional perovskite on top of three-dimensional perovskite? So the best way to compare this material is photovoltaic properties and stability. Now, if you look at the reference sample, our reference sample is having only 20% efficiency with VOC of 1.09. By changing or by depositing two-dimensional perovskite, that's a fluorophenylethylamine containing cation. So we increase the efficiency from 20 to 21% efficiency, and the VOC from 1.09 to 1.13. And if you replace the monofluoro to pentafluoro, the VOC increased further from 1.09 to 1.15, and the power conversion increased 21.65. But the small difference in the power conversion efficiency is very nice. However, if you look at the stability data shown on the bottom left side, the reference sample is decreasing significantly the efficiency over 1,000 hours per year. And the blue curve, that's a fluorophenylethylamine containing two-dimensional perovskite, and the pentafluoro containing one is the red line. So this demonstrates that using this two-dimensional perovskite as an encapsulant layer on top of three-dimensional perovskite, increasing the efficiency at the same time, increasing stability significantly. Now, I have taken another example here to demonstrate. That's a phenylethylamine. Here also, this is a phenylethylamine, but the two cations, the two substituents on the para position, and again on the meta position, and the ortho position. So if we use these cations, what happens? And if by using these cations, and if you take the para substituted one, this is the para substituted one, this is a characteristic peak of XRD peak of the two-dimensional perovskite, which comes around 6.5. 2 theta. So this is a para containing cation is forming the two-dimensional perovskite. Correspondingly, you can see the spectral properties, absorption spectra of the two-dimensional perovskite, the emission spectra, which is coming very close to 550 nanometers. However, if we go to the meta and ortho, it's not forming the two-dimensional perovskite, and there is no emission spectra. The absorption spectral properties are also quite different. And so just to remind, how does the two-dimensional perovskite looks? So this is the two-dimensional perovskite emission spectra. When we excite from the top side, you can see very clearly the two-dimensional perovskite emission peak. And if we don't have this two-dimensional perovskite, you can see only the three-dimensional perovskite emission. Using this configuration, as a control, we have a 21.94% efficiency. And the para-substituted one gives us 21% efficiency. And the meta-substituted one is lowering the efficiency from 21.9 to 19.6. And the ortho one is increasing the efficiency, reaching very close to 24% efficiency. So what is happening actually here is that we don't have to form a really the two-dimensional perovskite with the lead. Even these organic cations are sufficient to passivate the interface and giving the high efficiencies. So here is the best cell efficiency which I am reporting. That's a 23.92. That's a reverse scanning, and the forward scanning 23.27 with a small hysteresis. And this is a PowerPoint tracking over 250 hours. The efficiency remains quite constant. And the cross-sectional image is shown here. As before I mentioned, this is a conducting glass, and then we have a compact layer followed by the TiO2 tin oxide, perovskite, very thin layer of this cation deposited on the top of perovskite, spirometad, and the gold as a contact. And we also made a small mini modules, and using this type of configurations, you can see what is the beauty here is 40 to 50% humidity, 40 to 50% humidity. The reference sample is decreasing significantly compared to the ortho-substituted cation containing the perovskite solar cells. At the same time, the stability of 85 degrees temperature is required. The reference sample is decreasing significantly compared to ortho-substituted ones. But if you look at the unencapsulated under argon nitrogen atmosphere conditions at 25 degrees temperature under full sun, the efficiency remained intact over 1000 hours compared to the reference sample. So these are the conclusions which I have discussed before. So I just move on. So next topic for our discussion is composition engineering of perovskite layers. So as I mentioned before, the cations, methylammonium, this is formidinium, you have a 2 NH2 groups, and guanidinium, you have a 3 NH2 groups. So if you take these cations, and this is a tolerance factor, any cation which has a tolerance factor of between 0.8 to 0.1 can form the three-dimensional cubic perovskite zone. This is a three-dimensional perovskite zone. Now, if the cation size is bigger, this goes beyond the this cubic formation of the three-dimensional perovskites, and it forms a lower dimensional perovskite. And which is too small, it's not stable. So the guanidinium is a larger cation compared to formidinium, and formidinium is larger than methylammonium. The purpose of selecting these bigger cations is to induce the hydrogen bonding between the iodides and cations so that we have a high stability of these materials. Since you cannot form pure three-dimensional perovskite using guanidinium because it's a larger size, so what we have come up is, can we combine a larger cation to some extent and a smaller cation in a mixture of ratio of 3 to 1. So 75% is a methylammonium cation, 25% is a guanidinium. As you can see, these are critical simulations. So the bigger cation with the 3 smaller cations, they happily sit in the cubic unit. But the cell configuration is, as I discussed before, it's the same configuration, NIP. Now, if you look at the efficiency data, the black line is the reference sample over 1000 hours. Now the red curve is with the 25% of guanidinium with the 75% of methylammonium shows extremely stable performance compared to the reference sample. And in between, we have a 14 and 12.5% of guanidinium data. Now I come to the compositional engineering by doping inside the perovskite composition. So I come back to the problem of why should we dope? Because the perovskite has a issues of hysteresis. This hysteresis is a characteristic of the measurement system. When you are doing the reverse scanning and forward scanning, the curves, they are not overlapping. So this is because of ion migration and imbalanced charge extraction at the interfaces. So can we reduce this ion migration by bringing extra ions? So here is the strategy. So we are bringing extra ions. That's ionic liquid. Now we know this from our previous studies. the fluorine substitution protects your perovskite. Can we substitute fluoride groups? If you look at this ETI molecule, that's the imidazolium containing molecule, which has the fluorine substituted alkyl chain. So this is the ionic liquid we have selected, and by using this ionic liquid, let me just go to the panel E, where it's a expanded version. So what happens if you use a perovskite without this ionic liquid? You can see the presence of lead iodide. The presence of lead iodide is indication of instability of these materials. Now, if we use 2%, even 1%, you can see it's decreasing significantly, and 2% is a further decrease. Let's say if you take 4%, there is no formation of lead iodide, showing that the presence of this ionic liquid to the extent of 4%, you can make it extremely stable, that you don't see the formation of lead iodide. The rest of the characteristic features are the same, like absorption spectra, emission, and surface images. They are quite same. But if you look at the actual cell with 1% of this ionic liquid deposited, and this is the front side and this is the back side. On the left side, you can see the reference. Without this ionic liquid, you can see that it's a decolorizing. At the same time, on the back side also, it's a decolorizing. So it shows that this particular ionic liquid at ambient temperature, 50% humidity, it shows extremely stable performance. Now, question is, what is happening and how it is happening? So the data is shown here. The IV data is the photovoltaic performance is almost same with small differences. The best efficiencies are close to 20% efficiency with 1%. The reference sample is 19%, but in between we have this one data. So that's not important point which I want to highlight here. Actually, to understand what is happening with this ionic liquid. So if you look at the 1 grain, take 1 grain. Before we take 1 grain, let me give you the reference fluorine binding energy. You take any sample, fluorine binding energy, you get around 689. This is the peak coming from the fluorine binding energy. Now we take our perovskite grain and we, with the focused ion beam, we etch from the top to bottom. Now you see, what do you see on the top? We see at the top at 0 nanometers, the bifluorine binding energy at 688. And what do we see at 25 nanometers depth? We still see fluorine binding energy of this material. And at 50 nanometers, we have nothing. So what shows this experimental data is that we have this ionic liquid. When we are forming these perovskite solar cells, this ionic liquid is floating and they're forming a shell on top of the perovskite grains. That's how it's protecting the perovskite by hygroscopic attack. Stability data is shown here. The XRD data is very clearly demonstrated here at 60 degrees temperature. As the time goes on, you can see the formation of lead iodide is increasing from 0 hours to 720 hours. You can see the presence of lead iodide. This is an indication of decomposition of the perovskite material. But however, if you have only 1% of this ionic liquid in the composition, even after 720 hours, you can see very small formation of the lead iodide, but otherwise it's showing extremely stable performance. I take 2 more examples. One is a double bond containing the ionic liquid. The purpose I will show you here again. If we take all our perovskite solar cells, we are fabricating solar cells under nitrogen atmosphere in globose conditions. So can we make these perovskite solar cells outside? So the reason why we are doing this one is this ionic liquid can self-polymerize at heating at 80 to 90 degrees temperature. Since we are heating our perovskite solar cells at this temperature, this can polymerize. So we are using only methylammonium iodide, which is a less stable compound. At that time, the efficiency was very not high, 15%. By using this self-polymerizable ionic liquid, we increase the efficiency from 15% to 17%. The corresponding IV data and IPC data are shown here. If we change this composition perovskite to formidinium and methylammonium double cation perovskite, the efficiency increased from 17%, that's our reference sample, to 19%. But let me remind you, the data is obtained when you make the solar cells outside the glow box conditions. Now, if you look at the stability data, is shown here. with ionic liquid containing, that's a polymerizable ionic liquid containing the stability data over 2000 hours. The decrease in efficiency is around 10%. On the same time, similar ionic liquid, just to focus on the two structures bottom, one highlighted with yellow, that's a polymerizable ionic liquid. And the second one is a similar ionic liquid, but it's a saturated carbon. So if you look at these differences and to see that the efficiency, the stability data with the polymerizable ionic liquid, the performance is extremely stable. On the contrary, having the similar ionic liquid without double bond that polymerizes, that gives you very less performance. It's a 40% of the original efficiency. So that's a beauty of modification of these materials, either by fluorinated cations or self-polymerizable ionic liquids. I have one more example to show that here I'm showing another very interesting piece of information that when you are forming these perovskite thin films, usually they form uncontrolled crystallization process. Can we control the crystallization process by bringing ionic liquid that has a second functionality? What is that second functionality? You have a cyanide. Cyanide is a coordinating group. So it coordinate to the lead 2+ and slow down the crystal growth, and therefore you can control the morphology of this perovskite composition. So for that purpose, here we have taken 3 examples, one with a shorter chain, cyanide group containing one, with the longer chains with the cyanide groups, in another case, 2 cyanide groups with longer chains. And based on this data, the best one is a longer chain with 1 cyanide donor group, that's a coordinating ligand, gives close to 23% efficiency. If you want more details, you can find out this is a recent publication. Now the configuration is the same, NIP, and we have the even mini modules, which goes over 21% efficiency. And if you look at the stability, since our focus is enhancing the stability of these materials, so we always compare with the reference, that's our reference sample under similar conditions, and using these remaining 3 ionic liquids, the best one is with the cyanide and 1 long chain containing ionic liquid that gives you more performance, stable performance compared to the remaining 2 other ionic liquids. I turn my attention towards the development of charge transport materials. So as we know, we have 2 main charge transport layers, electron transport layer, hole transport layer. These 2 are weakest links in the perovskite solar cell, beside the perovskite. So what is the weakest link? When we use the pure TiO2 as the electron transport layer, now you see the efficiency over the long time period, 1000 hours, it's decreasing significantly. Now we went back and analyzed it very systematically. What is happening when we have a TiO2 and the light is passing through the ETL layer? So as time goes on, the interface between the TiO2 and perovskite is getting delaminated, and it's because of some oxidation process going on with the TiO2 and perovskite. Now, if we change the TiO2 to tin oxide, the tin oxide data is shown on the top. That's a red dots submerged with the blue dots, but just focus on the red dots. Now, if we take the pure tin oxide, this tin oxide gives you very stable performance. By combining TiO2 and then followed by the tin oxide, that's a blue dots data. So that shows this interface is very important. Pure TiO2 is not suitable. Either we have to use tin oxide, or combination of TiO2 and tin oxide gives you the best performance, and more details you will find in this publication. Now I come to a very recent publication. Still we are modifying our ETL layer. So in the previous study, what I have mentioned was this type of ETL layer. That's a nanoparticles, which has a LUMO level of the conduction band is -41. Now we developed a single crystalline TiO2 nanoparticles, and that has a slightly higher LUMO level, conduction band level. So that aligns much better with the perovskite composition, the perovskite layer, and the hole transport material is the same as the previous cases. Now using these 2 configurations, 2 materials, nanoparticles, which I showed so far, and using the newly developed single crystalline TiO2, and the efficiency we reached over 24%, and the nanoparticles one is at close to 23% efficiency. And using this new ETL layers, we also built these 9 cells mini modules. The 9 cells mini module gives you 10 volts VOC of the system, and the power conversion efficiency is reaching very close to 23. So here the beauty is that the smaller cell, that's a 24% efficiency, has a size of 0.15 square centimeters. Now here we have a size of close to 26 centimeters, 25 centimeters, but still the efficiency is 23. So in these perovskite solar cells, the take-home message is we have reduced the efficiency gap between the small cell and the larger cell. Now I come to the whole transporting materials. Now, if you look at the whole transporting material, so far we have used the spirometad, and this has a several issues. This is the whole spirometad, and the mobility in this spirometad is not very high. So we have to dope with the cobalt complexes. So it oxidizes the partially 10% of the whole transporting material to increase the conductivity. And also it has a lithium TFSI touchable pyridine. All these dopants actually promotes the instability of the whole transporting material. So can we change this whole transporting material class to a new class of whole transporting materials? This work is we just submitted. So here are the phthalocyanine. It's very nice compounds. Phthalocyanines, they stack together. So therefore, they may not require the dopants. So here we have taken two phthalocyanines, two types of phthalocyanines, where we change the metal center from zinc to copper, and the peripheral substituents, butoxy to alkyl, so that's a alkyl branched butoxy substituted ones. So these are the two various substituents on the periphery, and the central metal is the zinc and copper. So instead of going all through this data, the take-home message is when we are using zinc-based metal phthalocyanines compared to copper-based metal phthalocyanines, zinc-based metal phthalocyanines are showing best performance. And compared to the just butyl methoxy, butyloxy substituents is showing the better efficiency compared to the branched ones. So the data is shown in this table. So this zinc phthalocyanine is giving over 20% efficiency with the butoxy. This is the butoxy, and compared to the alkoxy in the same within the zinc family, 22. It's coming down to from zinc to copper 15%. Sorry. Zinc to copper, zinc to zinc with butoxy to alkoxy is coming from 20 to 15% efficiency. Now, can we get rid of this whole transporting material completely? So here is the one configuration. This appeared very last month. This is a joint work with the Fraunhofer Institute and our group. So we are collaborating on this topic. So here is the configuration. It's the same as before, that we have a conducting glass, compact layer of TiO2, mesoporous TiO2 layer. We deposited perovskite followed by the two-dimensional perovskite. But instead of depositing whole transporting material, here the carbon being deposited it acts as a whole transporting material, at the same time replacing gold as a contact. However, you have to pay the price because the efficiencies are not same as the previous configurations. And using this is the configuration, the two-dimensional perovskite structure is shown here. Here the cation is not the phenylethylamine. Here it's a octyl ammonium iodide cation we have selected. Using this configuration, the efficiencies is reached over 18%, and the stabilities are quite high. But a remarkable thing here is this is a whole transporting material free device giving very high efficiencies. So these devices are proven, and in our previous publication we have shown that the stability of this carbon-based perovskite solar cells remains 10,000 hours. So this is highly stable, reasonably performing solar cells. I come very quickly to the cost analysis of 100 megawatts perovskite the panel manufacturing process. So we have taken arbitrarily, there is no logic except intensity and the labor and cost wise. So we have taken one location, Egypt, the second location, Spain, and Poland and Switzerland. Now, if you take the manufacturing selling price in these 4 countries, these are Monte Carlo simulations based on the available materials in the catalog. This price can change, even it can go lower. This is on the maximum side. So 0.3, that's it, $0.3 per watt peak. If we fabricate this perovskite solar cell in Egypt, slightly higher in Spain, and Poland, it's slightly lower. In Swiss, it's slightly expensive. Now, if you look at the levelized cost of electricity, this can be between 3 to 4 cents per kilowatt hour in Egypt. Similar costs in Spain, in Poland can be slightly higher, and Switzerland can be slightly higher. So the take-home message is that the levelized cost of electricity can go down as low as 3 to 4 cents per kilowatt hour. Now, levelized cost of electricity again depends on the degradation and also efficiency. So here is the two curves. Yes, on the left side is the degradation. So if imagine our perovskite solar cells, the degradation is 2% per year. So the leverage cost of electricity goes slightly higher. If the degradation is 8%, this goes even higher, 12 cents per kilowatt hour. And if you look at the efficiency, since our small cells are giving 25% efficiency, the mini modules are between 22 and 23. So if you take this range, the levelized cost of electricity can be significantly lower. And the next slide shows the energy payback time. This is without installation on the left side. On the right side, it's a with installation cost. So if somebody installs 100 megawatts plants without installation cost, energy payback time can be less than 1 year. With installations, it can be 1.5 years of this perovskite. This is on the lower side. On the higher side, it can be 6 years, and on the left side, it can be over 2 years period. So with this one, I try to give some conclusions that say the 2D, 3D perovskite layers composition is very important to passivate, to protect the perovskite layer, and to reduce the defects at the interface. Now here we have plenty of opportunities to tune the two-dimensional perovskite cations. The students who are interested, they can further fine-tune the cation structure, cation geometry, and the steric hindrance. All these properties gives you new opportunities. And we fabricated the mini module. We reduced the gap between the small cell and the larger cell to a small extent. That's a smaller cell is 24%, and the larger cell is mini module is 23 with a small difference, and 1,000 hours stability with 95% retention of initial efficiency. So we have developed a single crystalline TO2 nanoparticles that I haven't discussed more details. Actually, the purpose of this single crystalline nanoparticle TO2 is to enhance the conductivity of these materials. As a result, you will see very enhanced the fill factor. All this aspect I have not discussed, but this is the beauty of these single crystalline nanoparticle materials, which increases the conductivity based on measurements done in Germany by Professor Vladimir. He has done the microwave conductivity measurements of these materials. The conductivity is very high. I would like to thank all my PhD students and the postdocs, and without reading their names, and collaborators throughout the world, and the funding agencies, particularly Swiss SNSF and the bilateral collaborations and Solarix projects, US Army, Toyota, Panasonic, and Cubic PV. This is the American company, and Horizon projects, QNRF, and Kiri projects. And thank you for your attention. I would like to express my gratitude to my group workers, and thanks to the organizers for giving me this opportunity to share our results, and I will be happy to answer your questions.
Thank you very much, Professor Nazeeruddin, for this very, very important topic. And you have made an overview of all materials and the related problems and challenge and the efficiency. I will ask Ustad Salim to take the floor.
Thanks, Prof. Ahmed, and thanks, Prof. Nazeeruddin. Now going to the Q&A, and let's check now if there is any questions in the chats, or who wants to raise his hand also to speak. Prof. Abdel Ilah, you can go ahead, please. Prof. Abdel Ilah.
Okay, thank you very much, Professor Nazeeruddin, for this very nice talk on these very hot topics of perovskite, hybrid perovskite. My question is about the stability using 2D on 3D hybrid materials, hybrid perovskite. For 3D, the orientation of the organic cation depends on the structure but also on the temperature. For the 3D materials, we have 2D materials, we have to make a big cation, organic cation, to make a difference between 2D and 3D to make stability of 3D materials. But in this case, the orientation of the material is not the same as for the 3D. The nature of organic cation is not the same, but also the orientation is not the same. What's about the effect of orientation of 2D materials, of the organic cation in the 2D materials on the stability of 3D materials, on the bulk one?
Okay, thank you. Very interesting question and deep understanding of this topic. This shows, so the question is, because if you take the three-dimensional perovskite, the conductivity in these materials, that's a carrier extraction, is extremely fast. This will not happen in two-dimensional perovskite. That's the question. That's the right way he asked this question. It's because when we deposit two-dimensional perovskite, the two-dimensional perovskite can grow parallel to the three-dimensional substrate. There we are having a blockage. Organic cations are non-conducting. So therefore we have a blockage. That's a conductivity is blocked. Now, can we design a new cations that gives me a specific orientation perpendicular to the three-dimensional perovskite? So that way I can have a fingers type of two-dimensional perovskite on top of three-dimensional perovskite. We are looking for the design of this cation. That's the reason why we are screening the steric effect, substitution effect, so that I can induce the vertical growth of three-dimensional perovskite. Now I come back to your previous question, is the two-dimensional perovskite is conducting? The answer is no, it's not conducting, but still we are extracting charges because maybe two-dimensional perovskite not completely uniform and conformally coated on top of three-dimensional perovskite, charges are still leaking. That's the first point. And the second, what is the influence of this two-dimensional perovskite on top of three-dimensional perovskite? Mainly it's a protecting. Secondly, the defects which you create, for example, it can be lead terminated, it can be iodide terminated, but lead terminated can form a two-dimensional link. So this way you reduce the defects. But there is a huge research to be carried out to control the orientation of the two-dimensional perovskite, to answer your question.
Thank you very much. Thank you very much.
Thank you, Prof. Ben Youssef. Okay, back to you, Prof. Ahmed Nawi.
Thank you. I have one important question regarding the industry and business. In your talk, and this is a very, very important, that you have did your R&D and your fundamental science in different direction, different materials, which giving different results. Do you not think that now you are in the status that you can choose one configuration, one structure where the industry can work and develop a prototype and etc. And I'm thinking about this carbon-based. When you use some carbon and there are some advantage, some pro and con. Do you think that is the right structure? Since the beginning, I remember when the Perovskite started, it was already giving some good results. Yeah. Do you think now you know in which direction, I mean, which configuration the industry should give money to develop?
Yeah, so this is also a very interesting question pertinent to the perovskite technology. So based on the knowledge and based on the literature data, I confirm your opinion that the carbon-based perovskite solar cell is the best option. NIP, carbon-based perovskite solar, is the best option. It's because you don't have hot transporting material, which is degrading the perovskite solar cell. Yes. But unfortunately, this particular IP is Chinese have, and the Chinese is already producing in a large scale production in megawatt scales using this configuration. The drawback is the efficiency you have to sacrifice. It's not a 25% efficiency, it's 18, but the stability point of view, this is the product which people or industrial partners can consider to go into the market in the beginning.
Okay, thank you. That's what I expect but I want to know this from an expert,
Yeah.
if it's true or not.
Yeah,
And
it's true. Other configurations still have issues. For example, NIP configuration, the whole transport material is a problem. In PIN configuration, the electron transport material is a problem. And the depositions also, there are issues. In these two configurations, the maturity is quite high, but the stability of the materials is not very high.
okay. One part of my questions also is, do you think the technology of inkjet printing or even drop on demand inkjet printing in order to make the material and also the device together, roll to roll, for example, it's an option or the best option, or we have just to be classic and to work like sputtering and all this kind of, and the weight processing together, etc.
Yeah, inkjet printing is a very nice option for large scale production. But the attractiveness of inkjet printing can be when we have surfaces which are curved. There the inkjet printing can have an advantage. And if it's a flat surfaces, maybe the cost of slot die coating is much cheaper than inkjet printing. However, there are specific areas you may have to deposit on curved surfaces and different surfaces, different designs. There inkjet printing can be a very good option.
Okay, thank you very much. And I really enjoy your talk always. It's you just learn a lot, quite a lot, and especially for students and labs which are involved in this topic, they have many options to work on it for PhD, etc. And you know that when you are doing a PhD, it's not just questions of to go to industries, also to the knowledge, to learn a lot. Thank you very much.
Thank you for your kind words. Thank you. Thank you.
Thank you.
Thank you, Prof. Nazeeruddin.